This meeting is being recorded, so I'm gonna leave, just kidding. Do you give me a green light?
Yes, I'm just checking the assessment schedule, but we've got most people. So I think green light is a go.
Okay, sounds good. So let's see, first of all, happy Friday. Good to see you all. Interrupt me at any time if you have an engineering joke, a new engineering joke. I want to say a couple general things. First of all, Mariah, if you haven't seen the post on Slack, we have filled the position for the stepwise program engineer. Mariah Henning is the person that we hired to fill that position. She officially started on Monday because she's already doing shadowing, basically an assessment. Today, she's not here to meet you all. I think she's met a lot of you in other meetings, but just know that Mariah's wanting to introduce herself and connect with you all and get to know the team. Probably next Friday is when she will join class. In the meantime, if you cross paths with her virtually or otherwise, please make a point to help me welcome her. We're really excited. Mariah is a IIAC alumni that graduated now almost 2 years ago. Michael, was she? No, you are 1 year ahead of her.
Yep.
Yeah. You'll hear from her more. There was something else I wanted to say about Mariah's background. Oh, she actually presented to class last fall on pumps and related efficiency topics, but I realized how many of you actually did not meet her already, just from the folks that we've hired this spring and so forth. So if you want to, by the way, just a side shout out, Blake's continuing to collect recordings that are really high value on the IIAC YouTube channel. If you haven't checked it out and you are wanting to spend some time to study up on IIAC topics, I would really recommend Mariah's presentation on pumps and related topics from last fall, as well as a bunch of other ones. But just realizing that we're adding to that list and you all are new already to these topics, a reminder. So Mariah's the one update. The second thing I wanted to make sure and say is please do keep Dr. Paul and I posted on summer plans and what you all have that's coming down the pipe. I guess in two ways. First of all, just in terms of your own availability, whether you're going to be doing other things full-time this summer, whether you might be available part-time this summer. And then the second thing is the reason we ask for that information is we do again plan to hire and have a summer cohort. So besides getting your information to inform our hiring, I also would welcome anybody making references to us, referrals like you've heard us say in the past. If you know individuals that would be great for this team, please, I think honestly the best way might be to connect them with Dr. Paul and I with an introductory email and say, I recommend this person and I'm copying them to introduce you. That probably is going to be more direct than even having them submit the application, because a lot of times we get applications and we don't necessarily connect the dots between people who are applying and people who are being recommended by the team. So making that direct connection is something that I would welcome. And Anne, standing offer before you exit left, I'd love to connect with more MBA students or business students in general. That being said, to date, Nestor and James and others have really put in some effort in our past hiring cycles to reach out to different organizations to get the word out to different classes. And they've all initiated that on their own. That is time that you are paid to do. And we love that initiative. So take my requests for referrals very seriously, whether it's on an individual basis or group basis. All that input is very welcome. Okay. The other thing I wanted to point out from last week that I didn't get a chance to talk about was I thought Chris Workman, who was our speaker on compressed air, did a fantastic job on technical topics. I also think he did a great job modeling some really important professional behavior that I wanted to point out. If you've been in a meeting with me this week in a group setting, you might have heard me say this already, but I think it's important enough to point out again to this full group. And in particular, it was around the sort of culture of transparency and how that relates to professional etiquette, I guess you could say. Are acting as a professional. You might recall from the presentation last week that there was clearly Chris is a very intelligent, well-informed professional who communicates really well. There was a point in the presentation where he fielded a question about a system related to compressed air that he didn't know about. And he was he was honest and transparent about that with confidence and without apology, which to me is fantastic behavior, professional behavior to build confidence and trust. And I thought if you didn't pick up on it, perhaps now that I've mentioned it, you recall it. That is by far a strong recommendation I have for you all as my responsibility to train you as young professionals and give you that first experience. I think a lot of times students in particular may not even realize it, but they'll feel pressure in certain situations to be the expert. And you're a student, first of all, so we know you're not an expert. Second of all, some of you are brand new to the topics that you're dealing with. So suggesting that you are an expert is somewhat disregarding to the professionals that are really experts. That being said, that transparency and honesty in a situation can go so far to building confidence and trust with not only your team, but your customer. So for example, a couple of situations, if you aren't aware of this, that I've seen this translate where students feel pressure to answer and probably make stuff up. And a lot of times I can tell when they're making stuff up, just so you know, is the situation where you're doing AR presentations and you may not have known how to proceed. You may not have had the time or, for whatever reason, you haven't been able to develop the information that you're presenting to the extent that you wanted to. Be transparent, be honest. Let's talk about how you can do that, and instead of how you are going to try to cover your tracks because you haven't been able to do what you wanted to do to date. A lot of times I'll see students present ARs and disregard them super fast simply because they just didn't get the time in to develop the idea. I can tell that. I don't like that folks default to that. Let's step back, let's communicate, and let's talk about where you're at and what's realistic to advance the idea. The other area where I see this happening a lot, and again, I realize it's a lot about pressure and trying your best to handle pressure, but when you're reviewing a report with a customer, the customer is most likely, and this is typically leads, as a student assessment leads, the customer is very likely to ask you a question that you don't know. For various reasons, because of the level of experience you have, because of who did the work, and you may not be as familiar with the details. It's totally acceptable to not know. What's not acceptable is to throw your team under the bus for some reason. Ultimately, as a lead, you're responsible for your team's effort. The other thing is not acceptable is to make stuff up. So again, being transparent, being honest, and in that particular situation, promising follow-up when you don't know something is by far the the preferred behavior there. So I just wanted to make a point to talk about that professional aspect of transparency and honesty when you don't know things, especially as engineers, just saying we all think we know everything and we don't. We're all human. That's all I'm saying. And being human is really a great way to build transparency and trust and confidence. Okay, enough of my pro tip for the day. Let's get on to the next pro tip. Michael, it's Lizzie is up for today, right?
Yes, Lizzie.
Great, thank you.
Okay, so today I am doing my pro tip on PV watts. And PV watts is a website that you can use to calculate an estimate of energy savings by installing solar panels on a facility. It's really nice because the website uses the location of the building to determine on average the weather patterns for the area and determine how much sunlight there is. And you can enter the size of the system and other location and logistical factors to get your overall expected energy savings. And it's just pretty simple and easy to work with. So as an example, I'm gonna do it with the Warnock Engineering Building. So I went onto Google Maps and I mapped the area of some of the best parts to put solar panels on the building. So basically just all the places where it's flat and there isn't a lot of shadows. And then I use that area to calculate the DC system size. This equation to get the DC system size is on the PV Watts website. And basically you just get kilowatts from taking your array area of solar panels, converting from area to energy and multiplying by the model efficiency. And a normal model efficiency is around 16%. It says that on the PV Watts website, and you can also find it on other sources online. So I took the area that I calculated from the roof and I multiplied that by 0.75 because the whole area won't be covered. And looking at the other buildings on campus that have solar panels, that's about how much are covered with that. So I got a system of 201 kilowatts. And then another thing that you can calculate with PV watts is the system loss. So on the left, this shows like the basic system loss that they give you. And depending on how much you know about the facility or the solar panels that you're installing, you can change that a little bit. But the biggest thing that I would change, just because we are in Utah, we do need to take into account the snow and the system loss because of snow. It doesn't have to be a huge loss because of snow, especially if the facility or campus just keeps the solar panels clean, but it would be a small loss, like 1 to 2%. And then, oh, this slide turned out funky. A good rule of thumb for tilt of the solar panels is to set the tilt angle to the latitude of the system's location to maximize the total electrical output. And for this building, it would be 44.77 degrees, and PV Watts does actually give you that value. And then here is a table of the total energy savings that the website gives you, and it breaks it down by month. And so you can use this to estimate savings using solar panels. And then I also have the website, so I will just walk you guys through that real quick. So you can type in like the address of the building. And then it will give you it will pull up the weather data, give you the latitude and longitude, and then this is where you can enter all your information. So we calculated a 201 kilowatt system. Over here, it has a bunch of information about what exactly everything means, and it gives you a lot of equations and just kind of explains it. So if you ever have a question about any of these, it basically gives you all the information right here. So it's very helpful. And then we can enter in the other values that we calculated, and then you can come down here and we'd be doing commercial. And then if you know like the rate from your facility, you could type it in there and then it will calculate the energy savings and dollar savings along with that. So it's a pretty simple tool. I think it's really helpful and really cool. Yeah, that's it. Does anyone have any questions?
Hey, Lizzie. Super cool presentation. I really like this website. Does it have any information or perhaps resources that we could go to for like implementation costs? And if not, do you have any idea we might be able to get that?
Yeah, so they don't actually have any implementation cost on the website, but I do have a couple sources that I've used, or I've done a previous AR that didn't work out, but I have some sources from that and about incentives, because there are a lot of incentives for solar as well. So I can put those in the Slack channel after this.
Yeah, that'd be great. Thank you.
Nice job, Lizzie. I'm curious where you already used PV watts.
Well, I used it on the Asahi assessment. We contemplated doing it because they specifically mentioned it, but they had a lot of objects on the roof, so we weren't able to get like a set array that would work on the roof.
Nice. And again, just so everybody knows, the website for the tool, which by the way, I totally endorse the use of this tool for these purposes, and it's a great fit in terms of the level of detail for IAC assessments. It's pvwatts.nrel.gov, right? Maybe you can just put that in the chat box as well.
Mm-hmm.
Fantastic. Looks like Michael's ready to roll.
Yeah, I just want to, what I'm worried about is whether the audio from the team will come through. So let me know if you're hearing Quinn's voice when I start it.
Thank you, Lizzie.
Hello, this is Quinn Alleman. I'm going to be presenting
we can
the
hear.
first half of the scope of work for Team QRS, which consists of myself, Rashid Bakar, and Sai Pandit. The main topics for our scope of work include power factor, air compressors, and Acfm and Scfm. So in engineering terms, power factor is simply the phase shift between the voltage and current waves. If they are in phase, the power factor is 1. If they become out of phase, the power factor drops. This animation shows the general behavior of how power factor changes as the phase shift changes. Power factor drops as phase shift increases. So listed here is the function for power factor. A power factor is the cosine of the phase angle. Shown in this picture is how both inductive and capacitive loads affect the overall behavior. In an inductive circuit, the current is going to lag behind the voltage, and in a capacitive circuit, the voltage is going to lag behind the current. Motors are inductive loads. That is why you install a capacitor bank to help fix the inductive load and correct the power factor. So the practical definition of power factor that you will deal with when working within the scope of energy management is the ratio of the actual power and the apparent power. The actual or working power is measured in kilowatts. This is the power that is usable. This could be the output of the motor shaft or other equipment. The apparent power is the product of the RMS voltage and current. This will all make more sense in the next slide. So this is one of my favorite analogies I've heard to describe power factor. The total volume of this glass is going to be the total power that has to be produced. While this may look like a lot, there may be a lot of foam. The foam is going to represent your reactive power. Although this power is generated, it is not used, and it will create heat in both the wires and equipment in the distribution system. This is why distribution and transmission equipment is often rated in kVA instead of kilowatts. The actual liquid part of the glass represents the usable power. The power factor is just the ratio of the total liquid to the total volume of the glass. If you have a motor that is too inductive, it will demand a lot more energy than is actually required. If the power factor is managed, the utility's total demand is reduced. I'm now going to hand this off to Rashid for the next section of this presentation.
Is the second part of the QRS energy presentation on compressed air. And I'm going to start with the third question, which asks, how does power factor change across load on induction motor? Across AC inductive models, the PF usually decreases as the reactive power of an inductive circuit is always positive. That is, or that means that in inductive loads, the currents are usually lagging behind the alternating current of the actual load. And its fourth question is, why does power factor matter more in an air compressor than other rotational machinery, pumps, fans, etc.? And the answer that we came up with is that in compressors, as opposed to other machineries, compressors have a periodically varying power and current with a substantial change in value. The varying load and current flow causes the current and voltage curves to constantly change phase, and therefore there is high reactive power across any compressor, making power factor an important factor for compressors. I'm gonna go to the fifth question, which asks, what is the difference between Acfm and Scfm? Acfm just means the actual cubic feet per minute, and Scfm means standardized cubic feet per minute. The actual cubic feet per minute covers the actual things that we see in the real world, while the standardized ones have made a lot of theoretical calculations and theoretical assumptions to come up with their values. And the sixth question is, how do you convert between Scfm and Acfm? Using the Acfm and Scfm can be converted using a formula that's not provided in our PowerPoint slides, and we will show it it'll be shown in the submission. And the last question asks that what variable do you think would impact the conversion of Acfm to Scfm? I would assume that based on the conversion between different types of temperature and pressure, like the saturation pressure, the absolute pressure, the standard temperature, the actual ambient air temperature, I feel like conversion between different modes of this temperature and pressure and different assumptions of these parameters would greatly impact the values that we get from converting from Acfm to Scfm. And I hope that I was able to make some sense with all of that. Thank you. This is the second.
All right, so did everybody get that from LLC4 from last week?
Tell you what, do something with your response in your screens, clapping or something if you did.
Wait, could you say the question again? My computer must have cut out.
Just want to make sure that everyone was able to see and hear LLC4 talking about their task from last week. Great. One thing I'd like to point out is the most important correction factor from a standard CFM to an actual CFM is the altitude you're working at, because the density of air decreases at a higher altitude. And that's something I'll mention today while I'm presenting. Anything else you wanted to note, Julie, before I start on commercial energy efficiency?
Nope, I think we're ready to roll, Michael.
All right. Well, welcome everybody. So what we're going to be talking about today is commercial energy efficiency, which is energy efficiency in buildings that are not manufacturing. And most of the IIAC has always been focused on small to medium manufacturers, but with the expansion of the Dominion stepwise program, and with potentially some additional commercial energy applications through the IAC, we may end up doing a lot more buildings that really don't produce a product or are outside of those standard industries that we work with a lot. And so we thought it would be a good idea to introduce the concept of how to look at energy efficiency in other types of buildings. And I want to start by recapping the videos that.
Hey, Michael.
Yes.
Can I add a couple things as you go here?
Yes, please. Please, anyone pop in with questions, especially if they're relating to a current assessment you're working on. Yeah, go ahead.
Awesome. So I also, just for the group, in case you need other reasons to pay attention to Michael's presentations today and next week for that matter, know that commercial energy efficiency is probably the more common and employable sector of energy efficiency. A lot of the work that is being done by energy consulting firms really focuses on this content. So Michael, case in point, will tell you about his own experiences as we go. Generally speaking, I would add the context that oftentimes for IAC students, there is this sort of leap between what you learn in school and what you learn at the IAC and what you might actually do in the professional world that translates to commercial energy efficiency. So what I'm saying in the end is if you listen today and next week, it makes you more employable. So just a little extra motivation.
And I would say that when I started working at Nexent after I graduated, I really knew nothing about commercial HVAC, which is going to be the majority of my presentation. It was something I learned in about 6 months to a year working at Nexent, but it is the majority of what we do. Moriah, on the other hand, where she was working at a different firm that was dealing mostly with extractive industries, she had a very different experience, but now learning about commercial energy efficiency should help you in your future careers, whether you go into energy efficiency or some other path. So I wanted to ask you all first about a recap of the engineering mindset videos that I had you watch. Do any of you have familiarity already with HVAC, or what was it that you took from those videos? What did you learn? Did you have any further questions, or how did you respond to those videos?
I thought those videos were super helpful. I didn't know really anything about HVAC systems, and I remember Julie would use that acronym a lot when I first started a couple months ago. So it was really good to see those videos and like to lay it all out, and then also not just lay it out, but describe the different sort of HVAC systems that there can be, and also their accents. It made it a little bit more entertaining to watch, so that was good too.
I figured he would do it much better than I could, so you're welcome.
Michael, I thought the videos were extremely useful and very well explained. And I found very interesting the part about the variable volume systems to handle different temperatures at different areas of a building.
Yeah, variable volume systems are going to be most common in large commercial buildings. Most of the smaller systems you're going to see, the rooftop units, are going to be single zone systems, and they may or may not be variable volume. But variable volume tends to be better for energy efficiency. Any other comments?
Nestor, as our fellow MEs in general should be particularly interested in this content. So Nestor, as a fellow ME, what was one of your takeaways?
Yeah, I think they were, well, kind of saying what everyone else has already said. They were really useful, and I've actually used the videos from that same channel in the past for non-HVAC related ARs in the past. So just as a heads up for the whole team, that's a good channel to reference just for other topics as well. Yeah, I think those videos give a really good like baseline for knowing the systems, and I think that add on top of it, we would just want to see these systems like actually in, in real life in the facilities that we visit.
So with that, I'm kind of going to move on, but we'll come back to the topics that you saw. Having that fundamental knowledge of those systems will help a lot with where I'm going today. So we're going to start really general with information from the Eia.gov. So what you see on the top left is sources of energy used in commercial buildings. And what you see at the right is electricity use in commercial buildings. And this is from the most recent data in 2012. So what I want to point out to you is the natural gas bar on the top left. Natural gas is pretty much exclusively used in commercial buildings for space heating. Maybe 5 to 10% of that will be used for water heating, but most of it is for occupant comfort heating. And then as we look to the electricity usage on the right, some of the major sources of electricity usage are familiar to us. So the lighting and the refrigeration might be fairly familiar to us. But as you see here, HVAC energy is going to comprise all of those heating that we see both from natural gas and from district heat, as well as from the ventilation, the cooling, the space heating, and some of that other bar. So what we're not seeing in that electricity use is that some buildings use electricity for heating. It's less common than natural gas, but when we talk about the total energy used by a building, a lot of it comes from natural gas, and that's almost exclusively for heating. Electricity can be more varied, but a lot of it is used for HVAC. And the difference between the ventilation and the cooling bars is what's used to replace the air that comes in and what's used to actually cool or deal with heat loss to the outside or the inside of a building. And then a lot of the distribution of heating and cooling through a building comes through fans and comes through pumps. So included in that other category is a significant portion that goes towards distributing heated and cooled or conditioned air through a building. And as you see, commercial is a pretty substantial sector of US energy consumption. So that's kind of where we're going. And when
Hey,
we
Michael,
talk about, yes.
Quick thing to jump in on. So from a conversation this week, that reminded me of this with our new hires in the spring of 2021. I realized that we are using acronyms like HVAC and other terms that aren't familiar. So just a heads up for you guys, when Michael takes a break in here, I'm going to facilitate a roundtable for each of you to mention some either term or acronym in this presentation that you don't recognize so that we can clarify those things. I know people are having questions and not asking, so I want to make a point to have that conversation.
And you can use the chat for that too. But if you have a question, type it in the chat, and I might not see it in the chat, but someone else will, I assume.
Yep, I'll back you up on that.
Okay, so when we talk about commercial buildings, we're talking, what comes to mind first to me is office buildings. So there are lots of those here on campus, or if you drive through the city, you'll see, lawyers' offices and all sorts of tech companies, banks. Those are all offices. Mercantile is any kind of retail, so a mall or a strip mall, some store that's selling something to you. Education can be K through 12 schools or college campuses. Healthcare, we often divide between the inpatient, which is the hospital, which is very different, and the outpatient or the medical office or the clinic, which isn't so different than just a typical office. But there's a major distinction between the inpatient and the outpatient care. And as we get down that list, there's an incredible variety of commercial buildings, that aren't being used to manufacture something. And all of that falls under the realm of commercial energy efficiency. So let's talk about some of the loads in these buildings. And we're going to start with the easy ones first, the ones that we're familiar with. The lighting, the refrigeration, the compressed air, and then go to some that we might not be as familiar with. So the computers and the HVAC, which is the heating, ventilation, and air conditioning. So the things that should be fairly familiar with, or that I'm not going to go into a whole lot of depth today, are lighting, refrigeration, and compressed air. there really is nothing that new about lighting in commercial buildings. Everything you already know about lighting still applies. We're always going to be recommending upgrades to LEDs. They're much better than compact fluorescents or incandescents. We're going to be recommending the same lighting control strategies. We're going to be recommending daylighting, occupancy sensors, timers, and schedules. One thing to note about schedules is that most commercial buildings operate on very fixed weekly schedules. Usually, the operating hours of the store are posted, and employees might be present for an hour to a half an hour before they open, and maybe half an hour to an hour after they close. But those are pretty standard, and lights should reduce significantly when the building is unoccupied. Most buildings prefer to keep some fraction of their lights on overnight for safety and to discourage people from loitering who aren't supposed to be there. Refrigeration, we're really only going to find it in grocery stores, refrigerated warehouses, and to a smaller extent in food service and restaurants. So a grocery store obviously has large refrigerated cases and frozen cases for their products. And if it's a warehouse that's serving a food distribution industry, that might be similar, just to keep perishable food from going bad. Pretty much every restaurant or convenience store is going to have a walk-in cooler and a walk-in freezer. But in buildings where there is refrigeration, it's a major load, but most buildings don't have refrigeration. And that's going to be pretty similar to our refrigeration knowledge for manufacturing and industrial facilities. So I'm not going to go into a whole lot of depth about that today. And another one that doesn't need a lot of discussion today is compressed air. There really is only one use for compressed air in most commercial buildings, and that is to run a pneumatic instrumentation control system. What you need to know about pneumatic controls is that they are completely obsolete. The only recommendation for compressed air in most buildings is to get rid of it. And the solution to that is to replace it with a direct digital control system, or a DDS system. And direct digital controls are superior because they offer quicker response times, a lot more controls capabilities through them, and they don't require this continuous energy input. So, and you might find some buildings that have maybe a small air compressor for a tool shop or for a boiler room, but those won't be major uses of their energy. So compressed air isn't something we need to talk about very much. One thing that you might not be familiar with, but that's still fairly minor, is the concept of plug loads and computer stations. So as you think into a typical office building, they're typically comprised of cubicles or workstations that include a computer, maybe some monitors and other peripherals, and anything someone might plug into a wall outlet. So coffee makers, desk lamps, the appliances in the break room would go in this category. And these aren't things that are quite as easy to break out by end use, but they just kind of go into this broad catch-all category of plug loads. So one thing to point out with this category is this concept of ghost energy. And ghost energy refers to things like computers and monitors, and maybe at your house, your game consoles or your DVD player or things like that, that instead of turning off, they go into a low power standby mode. So they're still using a small draw of energy, even when they're really not actively used. And if you multiply that over hundreds of cubicles in an insurance office, say, you might end up with substantial power draw, even when nobody's working, maybe all night or when half of the workforce is out or something like that. So one way to address the ghost energy problem is with a smart power strip. A smart power strip will have a control outlet that goes, say, to the primary piece of equipment on a desk, like the computer. And then when that primary piece of equipment is turned off, it will power down all of the other sockets. So if you imagine this at your home, you might have your television plugged into the control outlet, and then you might have your PlayStation plugged into one of these automatically switched outlets, because when the TV turns off, the PlayStation won't need any power. And that prevents this ghost draw. A lot of smart power strips will have some outlets that won't automatically switch off, which will be those constant hot outlets there on the right. So that's a way to deal with the solution. I wouldn't really recommend doing this without getting the buy-in of your IT department. Sometimes it's not a good idea to switch off computers overnight entirely. So to work through computers and plug loads, the measures that we would recommend are more institutional and behavior-based. We would work with an IT department or a facilities department to manage the device power, maybe install these smart plug strips. And a lot of it also has to do with choosing efficient appliances and just minimizing the amount of power that is used. And a common example of that that's happening all over is people are choosing to use laptops instead of desktops, both for the portability and for the energy savings. And so individually, these kinds of measures don't result in much, but together they can add up. And so there is a resource down here from the Government Services Administration looking at how some of these large buildings can optimize their plug load uses, but we're going to move on from there. And now we're going to start talking about HVAC energy loads. So maybe before we get to there, are there any questions or comments up to now? Sounds like no.
I have a quick question. So is using a smart plug or that, like you're just showing, the best like energy saving way to address the plug loads?
It can be. This is useful for like a computer or a TV setup. It might not be very effective for the coffee maker and things in the break room. It might not be very effective for the lamp on your desk, So it's kind of hit and miss. It can be useful for certain applications, but there isn't like a way to fix all plug loads immediately, except by purchasing more efficient equipment and appliances and by managing how often and how long they're used.
Okay.
Yep.
Kind of related to Sam's question, it seems like the margins on this AR would be kind of slim. Is there some option where maybe you could put in a control scheme for the entire floor of the building? Say from like 1 to 4 a.m., it just completely cuts the power access? It just seems like the savings would be pretty marginal.
Yeah, the savings are very marginal. And you would probably have to do something like that at the level of the electrical panel. And you might include things that you really do want to stay on all night, like the certain fraction of lights or the automated door system, the security system. So usually they don't recommend going that far to search for plug load savings.
But that is increasingly a practice in new construction to be able to organize those circuits and panels. Conrad, exactly to the point that you're making, that type of control on a building level basis through an automation system or something is possible.
All right, so let's go to HVAC energy loads. So heating, ventilation, and air conditioning is driven entirely by people and the weather. And by people, the extension of that is the equipment they need to do their jobs. So both people and computers are heaters. We, as part of the food we eat being burned to keep us alive, produces a little bit of sensible heat, which is sensible heating is the direct temperature raise of a piece of air. So people and computers give off heat. People also breathe and sweat depending on their activity level, which gives off a latent load, which is the water that we put into the air. Water comes out of every breath we take. And so that is something that the HVAC system has to respond to remove that water load from the air. And because we need fresh air, an HVAC system has to ventilate and bring in fresh air to replace the air that we're breathing. And then when it's hot or it's cold outside, we'll get heat gain and heat loss through the walls, windows, and roof. So HVAC systems are designed to keep people between optimal comfort levels, which tends to be about 68 degrees to 74 degrees and about 40% relative humidity. And some facilities might have a more specialized requirement for their conditioned space. Something like an archive or a data center might have a very tight tolerance for the relative humidity. Hospitals, laboratories might need more ventilation. So other things can have more specialized requirements. And it also depends on the degree of the activity of the people who are in the facility. So a gym is going to have people doing very heavy work. They're going to give off a lot of body heat and a lot of latent heat. So they are going to have a more efficient HVAC system to deal with all of those types of activities in the building. Offices tend to have people doing light activity, and so they don't give off quite as much heat as part of their daily routine. And this topic is called psychometrics. So the relation between latent and sensible heat in the air is called psychometrics. And there's a very useful but complicated to read chart called a psychometric chart that HVAC engineers use extensively.
Michael, some people on the channel might remember Sunny from KW presented, maybe two years ago now, and came in and gave his best pep talk to get people interested in psychometrics. So it's a big deal. It's not something we go into, but Michael's doing a good job to touch on the high points here.
So when we talk about buildings and ventilation, buildings are boxes, and the walls, the windows, and the roof are insulated to an extent to keep the conditions inside nice. So the dividing line between outside and inside is called the building envelope, and it serves to keep rain and snow out, it serves to keep the wind out, and the nice, cool, conditioned air inside. So any penetrations inside the building envelope will allow air to get in, or air to get out, or water to get in. So commercial buildings typically have a mechanical ventilation system. There is equipment that is bringing in fresh air. So this is different than your house, which doesn't have a mechanical ventilation system. It just relies on the air seeping in to keep it well ventilated. Ventilation is governed by local code, but that code is influenced by a publication from ASHRAE. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. So in their publication 62.1, they specify that ventilation needs to be calculated based on the area of a zone, the number of people in a zone, and then specified rates of ventilation per person and per area. And that's found in ASHRAE 62.1. You can look up equation 6.1 and table 6-1 for all sorts of building types and uses. Now, it's critical to know that ventilation is critical to safety in certain applications. So control and safety of hazardous fumes is a very different ventilation scenario, and it's not addressed by this code. That's very specialized, and so don't apply this to a hazardous or a critical application.
Quick note on that. That exact topic has come up with our wastewater assessment. We're looking at some HVAC recommissioning ARs, and the code relating to specifically wastewater buildings is actually specified in, it's called the NFPA, I think the National Fire Protection Agency. And yeah, exactly to Michael's point, there are some potentially toxic and flammable fumes that are in these facilities. So just be aware of that.
Yeah. So there is a whole profession of engineering that is mechanical design. And those are usually called MEP designs. There are several MEP firms around the valley that are mechanical, electrical, and plumbing design firms. So an engineer at one of those firms is tasked with calculating heating and cooling loads, taking into account how many people are going to be in a room, what kind of equipment is going to be in that room, and how extreme the weather will be at the peak design condition. So on the right is a weather forecast for Salt Lake City taken from the ASHRAE Handbook of Fundamentals. So for Salt Lake City, we anticipate that 99% of the year, the temperature will be at 14.4 degrees or higher. So a year is 8,760 hours. About 87.6 hours of the year will be less than 14.4 degrees Fahrenheit. Simultaneously, we estimate that 1% of the year will be higher than 95.4 degrees Fahrenheit. So an MEP engineer will use those extreme temperatures to decide how big and how powerful the cooling equipment and the heating equipment needs to be for a building. So you'll see here that we're talking about a heating dB. dB is a dry bulb temperature. And dry bulb temperature is the temperature we're all used to feeling. That's kind of the standard normal temperature. A WB temperature is a wet bulb temperature, and a wet bulb temperature relates to the amount of water in the air. So at 100% relative humidity, really, really hot, really muggy, the air has as much water as it can hold. The wet bulb and the dry bulb temperatures will be the same. So the difference you see here between the dry bulb of 95 and the wet bulb of 62 shows that we're not very humid here in Utah. And that's a characteristic of the climate region that we're in, which is dry. So as the relative humidity approaches 100%, the wet bulb temperature will approach the dry bulb temperature. And those are both important factors in psychometrics to sizing and designing a system. So usually, for our purposes, it's enough to go out to the HVAC equipment and look at the nameplate, find the size on the nameplate, and assume that the engineer did their job right, and they designed the system to be large enough to accommodate the peak load, plus a certain extra. Engineers will always add a 10 to 20% cushion to make sure that they're never wrong, to make sure that it will always be able to handle. And I see Sammy's question. So the reason for the exact temperatures of 14.4 and 95.4, that is historical climate data taken from the Salt Lake International Airport. So ASHRAE, or NOAA, I think, Atmospheric Association, has compiled historic averages of weather and climate for Salt Lake Airport and for hundreds and thousands of other data points in, and they've looked at the average temperature and say, on average for this location, it'll never get hotter or colder than this. So you do want to find the most specific weather station that you can find. So this is just for Salt Lake City, but there will be another one for Ogden, another one for Provo, another one for Park City, another one for St. George. So basically, just look at how big the boiler is, how big the chiller is, and assume that it's 10 to 20% oversized, and that'll be kind of your maximum cooling load, assuming it's only used for cooling the building. So quick review right here before we move on to kind of the equations. We have an air distribution side, which has fans to send air into the building. Return air is exhausted or recycled. We're bringing in outdoor air to ventilate it. In an air handler, you have a heating or a cooling coil to adjust the temperature before it's distributed to the building. And those coils might also humidify or dehumidify. And then on the other side of those coils, we go back to the plant, which will have either a chiller or a heat pump or something to extract the heat. Separately, there will be a heat source like a boiler or a furnace to pump heat in. And then through those coils, the heating or the cooling is distributed into the air and then into the building. Is everything clear before we dive in? All right, let's go. So thankfully, there aren't that many equations to use. So for air, we're basically just using an m c sub p delta T. So the energy required to raise an air in sensible heating is 1.08 times the volume of air times the temperature difference in the air. We have to throw on an altitude correction factor because we're at a fairly high elevation and air is less dense at our elevation. So for sensible heating of the air, we do this. For latent heating, so extracting water and humidifying or dehumidifying, we use that equation. Thankfully, we're at such a generally dry environment that we very rarely run into this calculation in HVAC building systems. So usually humidifying or dehumidifying isn't required for general offices. Now, if we're heating or cooling water, we have a very similar equation, a density times a specific heat times a time conversion times the volume of flow being heated or cooled times the temperature difference, what we're raising it to and where it started, will give us the BTUs per hour. We don't have a correction factor on there because water doesn't change density with altitude. And then if we're using pumps and fans, there's a set of equations called the affinity laws that tell us how speed is related to energy to pump and is related to the pressure drop required to pump something through. So these are very, very useful equations. And oftentimes for a VFD, we will use these pump affinity equations to estimate how much we can back off the power by reducing flow through a pump. So if you're at 100% and you reduce it to 70%, your power is being reduced by 0.7 to the third power. So it goes way down out of proportion to the reduction in speed. I've seen it in my professional experience derated to 2.7 or to 2.5. So that's optional. There's not a great intuition for why that is, but I have seen it happen before. And if you're trying to calculate brake horsepower directly from the system, you'll use an equation just like this. So volume times the pressure drop times a conversion factor of density and specific heat times the efficiency of the pump at converting electrical energy to mechanical energy. I don't use these very much. It's basically just an affinity law and one of these. So the air handler systems that you looked at include ventilation, and that's an important topic that we're going to talk about. So usually outdoor air dampers are fixed unless there's some kind of more advanced control system. I've most commonly seen them fixed at about 10%. So about 10% of the air going out through the supply air duct comes in through the outdoor air dampers. Most of the time, air handlers recycle the remainder of the air. So that means about 90% of the air, or whatever 1 minus this percentage is being recycled from the building. It's coming in at the temperature of the building. Usually that's the thermostat temperature plus 1 to 2 degrees Fahrenheit because it is taking the load from the building and removing it. And it's also a little bit stratified when you get into a room. So the return air is mixing with the outdoor air, and you're getting a mixed air temperature that's basically a weighted average of the outdoor air and its temperature and the return air and its temperature. And that mixed air temperature is what you have to heat or cool to meet your supply air temperature. So usually buildings set their supply air temperature set point to be 55 degrees Fahrenheit when it's warm outside and 60 degrees Fahrenheit when it's cold outside. And those are recommended by ASHRAE and other publications of theirs. And most air handlers have a supply fan and a return fan. The fan speeds for those, if they're variable, are going to usually be about the same, so they'll both be at 90%. But the return air fan motor is generally always smaller. So if your supply fan is a 25 horsepower fan, your return fan is usually 10 to 15 horsepower maybe. So it's smaller, it's running at the same speed, it's exhausting about the same amount of air. It's usually about 90 to 95% of the air volume that's going out the supply is coming back the return. and the rest of it is lost through leaks in the building. It seeps out the doors. If this return fan is being controlled to a different speed setting, it's usually modulating to maintain a pressure in the building. So usually right above the lobby in a building, they'll have a pressure sensor to make sure that the building isn't overpressurized. And if it's overpressurized, the doors might be blowing open, or they might be hard to open because they're trying to suck in. So that directly impacts how easy it is to open the doors. So now we're going to shift from the distribution to the heating and the cooling plant. Most of the time, we're going to see either an air-cooled chiller or a water-cooled chiller in a larger building. I think you saw that in the engineering mindset videos, that one is cooled with air, the other is cooled with water through a water tower. So an air-cooled chiller will have lots of small fans, and it will be located outside. A water-cooled chiller will have 2 barrels, and will be connected. One of the barrels will be connected to a cooling tower, which will always be outside. And the other barrel will be connected to the building pumps and will be inside, usually on the lower floors because they're very heavy. And then a boiler, I think we're pretty familiar with boilers, and some of the graduate students will talk about those more later. Some other things we might see, a rooftop unit is just a packaged gas heater and a refrigeration system all in one box. And they just plop these down on the roof. I think you saw a little explanation of that at the end of one of the videos.
I'm going to check and say this package that he's talking about right now is definitely the most ubiquitous application for HVAC. And also, if we have spaces that are office spaces associated with our manufacturing plants, most of the time they're going to have this equipment.
In large office buildings, and more commonly nowadays in Utah, we're going to see variable refrigerant flow heat pumps. That's a pretty complicated topic. They are heat pumps, so they use electricity for heating and for cooling. So I don't want to get into that a ton right now, but if we have time next week, I will. They'll have a condensing unit on the roof and then little cassettes throughout the space. And then another thing we might see a lot in Utah is a swamp cooler or an evaporative cooler, which doesn't use a refrigeration cycle at all. These are very energy efficient because there's no compressor at all. They're just evaporating water and using that temperature drop to cool the space. And we are able to do that because it's so dry, not humid in this region of the world. So most central plant equipment is rated in kilowatts per ton. A kilowatt per ton is the input power in kilowatts divided by the ton of refrigeration it's delivered. And a ton of refrigeration is a unit of energy. It is antiquated. It goes back to the days when ice was used to cool things, and it's related to the amount of energy it takes to cool a ton of ice in 24 hours. But it's defined as 12,000 BTUs per hour, or 3.5 kilowatts. And you'll see that all the time. A lot of systems like heat pumps and some chillers can be rated in a coefficient of performance, or a COP, which is unitless and basically just a ratio of the energy out to the energy in. And small systems like a rooftop unit or your home's air conditioner are going to be rated in an EAR, an energy efficiency ratio. And that has units of BTUs per hour applied versus the electricity that goes in. The nice thing about kilowatts per ton, COP, and EAR is that they're all pretty easily convertible. And there's a useful calculator on abraxasenergy.com that I use all the time. So for these systems, lower kilowatt per ton means it's more efficient, a higher COP is more efficient, and a higher EAR is more efficient. But all systems will perform differently at full load and part load conditions. As we kind of discussed earlier, most systems are only running at full load for 1% to 2% of the year at most. And because of that, we have to look at seasonal averages. So there's a variation of the EAR called a SEER, which is a seasonal energy efficiency ratio. And all the time, basically every chiller and heat pump is going to have some kind of part load value, whether it's an integrated part load value or a non-standard part load value. And an IPLV and an NPLV are basically the same metric, just evaluated at different conditions. ASHRAE has a very distinct standard for the IPLV rating, and it's a function of the condenser water temperature and all sorts of other things. So if it's been evaluated at those specified conditions, it's an IPLV. If it's been evaluated at other conditions, it's an NPLV because it's at non-standard conditions. But either way, they use the same breakdown for the efficiency weighting. So they weight it 1% at the full load efficiency, 42% at the 3/4 loading. They rated at 50% loading, 40% of the time at 50% loading, and 12% of the time at 25% loading. And that gives you kind of a curve that looks like this. And as you can see, it's most efficient when it's partially loaded. And then this chiller gets less efficient at higher loads and less efficient at lower loads. And what you'll see here, the solid line is for a variable speed chiller. The dotted line is for a constant speed chiller. And the different colored lines are the temperature of the condensing water entering the other side of the barrel. So all of those just go to show that it can be very dependent on the conditions it's actually running at. So just look for the published efficiency of the chiller. Use the IPLV or the NPLV if you know it. And if you are really stuck, the best resource to ask is a chiller manufacturer or distributor, because they have advanced software that calculates those really, really accurately at all sorts of conditions. Otherwise, it's really hard for us just to do that ourselves. So for heating, we basically just use a boiler or a furnace if we're using gas, and they have a combustion efficiency that I think we're pretty familiar with. And this will be covered more at length in a future presentation by some of the other graduate students who will talk about boilers. Just know that boilers and furnaces are either non-condensing or condensing. Condensing boilers recover more heat and are more efficient because they extract the water that's going out in the flue gas. If you're using electrical heating, there will be a heating specific COP or an HSPF, which is a heating season performance factor. One interesting thing to know is that a good heat pump can deliver 3 to 5 times more energy than it's used to run it itself. So it has a 3 to 5 COP. Electric resistance heating will always have a COP of 1. You're simply transferring it directly. And so I did a quick example over here to show the energy cost and the dollar cost of an electric resistance pump, an electric resistance heater, a heat pump, and a furnace. Just to show that it might be more expensive on a per energy unit basis to run an electric resistance heater than something comparable. So electric resistance usually is not a very good heating system. We'd rather use something like a furnace or a heat pump. And a good heat pump can compete with a furnace or a boiler based on the outcome of the cost to run it. And one other thing to note is that heat pumps don't create heat. They only extract it from one location and move it to another. So in a cold climate, such as Salt Lake City, in the winter, heat pumps just can't extract that much heat when it's 10 degrees Fahrenheit outside. So their efficiency goes down a lot when it's really cold. And they'll often have a backup heating source like resistance or a gas burner. So steps for an HVAC analysis, I would recommend the bin model, which takes climate data and sorts it into hours per year. And one of our LLCs is going to develop this more for us next week. So I won't go too much more into that. But it's after that, a heating or cooling load profile will say that at the hottest day of the year, the hottest hour of the year, your system's probably going to be working at 100%. And that's going to ramp down as we get to a colder temperature. And I have seen it very commonly assumed that that ramps linearly down to the temperature when you don't need any more cooling and you switch over to heating. And that switchover temperature is generally 55 degrees Fahrenheit or maybe 60 degrees Fahrenheit, somewhere in there. And then once you know that heating load profile and that cooling load profile, then you can do your energy analysis. If you know the efficiencies and the use and the hours of your equipment, you can do your energy estimate and then compare it with energy data that you actually have to show. We can always look at summer bills to show how much more energy they use during the summer to get an estimate for their HVAC energy use. If we have logger data for fans or pumps, that's very helpful. It's always helpful to normalize it or regress it against the outdoor air temperature. And it's always helpful to filter it between an occupied and an unoccupied status of the building. So that's kind of where I want to leave it in terms of energy analysis. Do we have questions? And then I'll get to the LLC tasks.
I did have one question.
Yeah.
So in our assessment that we're working on, the AHUs that control some of the HVAC to some of the buildings, their control is based off of ACH, air changes per hour. For some of our ARs, we need to know what that ACH is. However, the facility didn't know like how to access that data from their SCADA system. So what our team is thinking of is somehow calculating that ACH, but to do that, we need to know the flow rates from the supply and return air fans. Is there like rules of thumb or methods to calculate that CFM, given that we know the size of the motors powering these fans?
There are rules of thumb for the CFM per motor horsepower. Those are very rough. If you have nameplate data for the ventilating equipment, I would probably look at that to give you an estimate and assume that some fraction between 5 and 15% of the total flow is going to be outdoor airflow at any given time, unless they have a more complex ventilation control system.
Awesome, thanks.
Yeah. Other questions?
I was just gonna ask, so in the past I've seen that heat pumps can also use heat from the ground instead of outside air, as it's usually warmer. Have you seen that being used in Salt Lake City, and how efficient has it been during the winter?
It's much more efficient during the winter, and in fact, it has been used all over. Weber State has multiple campus buildings that are connected to ground loop heat pumps. What's the brand new building right in front of the Marriott Library? That has a ground loop heat pump system. So it happens all the time.
I put a link in the chat, Mateo, to the company that did the Weber State project.
Okay, I'll take a look at it. Thank you.
Yep, it happens. It's happening regularly for big projects. Other questions? All right, so let's talk about LLC tasks. So I'm going to put this up on the Slack channel and on the Canvas page later, but MNL Consulting is going to explain to us a little bit more about recommissioning, which is kind of an umbrella term for looking at a building and fixing everything that's drifted, fixing everything that just isn't happening the way it was designed. So they're going to identify and present one energy conservation measure per person under this umbrella of building recommissioning. I want them to make sure that each ECM is unique, but they shouldn't look at the two measures that are being handled by other LLCs specifically. So Nestor, this would be a great chance to talk about several of the ones you're seeing at the Central Weber wastewater plant. And then another hint I have is to look at the monitoring-based recommissioning approach, and there's a new incentive program from Dominion looking at that. So something interesting if you're curious. The energies are going to look at ventilation and present to the class what a demand-controlled ventilation system is and how it works to save energy. I've left you a link right here that you can start at. I also want them to explain to us why CO2 is commonly used to determine occupancy and adjust ventilation, and what are some of the set points they use for that. And if they have time, because this is 1 hour per person, since you've already used 1 hour to watch those videos. So shorter than other weeks. So if you have time, what equipment, techniques, or procedures can the IAC use to determine if a commercial area is overventilated? So experience energy is going to show us a bin hours generation scheme. So the IAC has access to a software tool called Bin Maker. So I would like you to show us how to generate a bin hour analysis using Bin Maker. And I'd like you to prepare a template bin hour model for Salt Lake City, put it on the box, and show the class where to find it and how they could use it in a future assessment. And so that'll be Tess and her group. And Tess, you already have some familiarity with this, so have you do that. YA3 is going to do some outdoor air economization looks for us. So I want them to figure out what is an outdoor air economizer and how does it work to save energy. And I have a link here so this first link, do read it. It's useful. It's from Train, which is one of the big names in air conditioning equipment. Your second task is to answer for us, why is a fixed dry bulb temperature the recommended control method? And there is a link here that you don't have to read. You just have to read the conclusion and table 1 and table 2, skim everything else. And then if you have time, develop a guide or a cheat sheet to help future IAC students working on an economizer related recommendation. And then QRS Energy Consulting, who are all off on an assessment today, I think. They are going to demonstrate for us how to get degree day data from degreedays.net. And this is a useful metric for determining just how hot and how cold an area is. And they're going to explain to us how to normalize heating or cooling energy using degree data. And if they have time, how can a degree day data analysis create a baseline for energy consumption? All right. Thank you very much. Any further questions?
Michael, I got one for you.
Yes.
So for any of you that don't know this, Michael just gave us an amazing version of HVAC crash course in 1 hour of many topics. He covered a lot of ground there. So, you know, Cliff Notes versions that you just got a fantastic tour of the Cliff Note versions of HVAC. I have a resource that I want to point out to you. So Michael, thank you for that. I want to point out a resource to this group as a reminder before I forget it. But Michael, my question for you before I say that is, in your transition from the IAC to commercial building energy work, what was sort of the top 1 or 2 resources, ways that you used to learn about this topic?
The engineering mindset was probably the #1 thing.
Okay.
For me, seeing 3D visualizations of things was very helpful. My company, Nexent, had several in-house resources. So there is a class on these topics at SLCC, and I think there used to be one still in the mechanical engineering department. Maybe an ME student can check on that for me, but at least there used to be. And then a lot of experience, really.
Yep. Great. You actually started to make the point that I wanted to tell everybody. Personally, I took HVAC in my ME curriculum. I had 1 or 2 classes in my undergrad degree to get my undergrad degree. Like Michael, my experience for HVAC was a lot around actual experience, especially around commissioning of new buildings as well as recommissioning of old buildings.
And commissioning refers to going into a building, checking the set points, making sure fans are meeting the set points, responding correctly to the sensors, just making sure everything works the way you think it works, because things don't always work the way you think they're working. And especially as time goes by, things get out of calibration, and etc.
And the thing I wanted to particularly point out is for any of you that are thinking about going into industry and staying focused on energy efficiency and trying to broaden into commercial energy, the U actually right now does not have HVAC classes. They used to have a little bit, but they actually don't have any professors in the ME department that focus on this topic. But a reminder, Michael mentioned it too, SLIC does have associated classes. So even 1 or 2 classes in that commercial building energy space is something that I would highly recommend. Again, if you're thinking about after graduation, going into this commercial energy space. So thank you, Michael. Great job. It sounds like we got all of our next steps for next week planned out. So happy Friday to everybody. See you next week. Bye-bye.